Hello everyone, welcome to the course of ultrasonic testing technology. The main content of this course is the quantitative method of ultrasonic testing defects. Through the study of this class, we hope to achieve the following teaching objectives. Grasp the meaning of ultrasonic detection sensitivity. Master the classification of adjustment methods of ultrasonic testing sensitivity. Grasp the meaning of defect quantification in ultrasonic testing. Grasp the classification of ultrasonic flow quantification methods. First of all, in the process of ultrasonic testing workpieces, we need to adjust the detection sensitivity before defect quantification. So what is detection sensitivity? It refers to the ability to find defects of specified size within determined sound path range. The detection sensitivity generally needs to be determined according to the product technical requirements or relevant standards. The adjustment methods can be divided into test block adjustment method, curve method, and workpiece bottom wave method. Test block adjustment method, for example, ultrasonic flow detection of a steel forging with a thickness of 100 mm is not allowed phi 2 defects of equivalent size of flat bottom hole. The adjustment method of its detection sensitivity is to process a piece with the same material, surface roughness, and sound path as the inspected forging phi 2 flat bottom hole test block. Aligning the probe with the phi 2 for the flat bottom hole, the instrument retains a certain attenuation margin, and adjust the attenuator to phi 2 with the highest echo of the flat bottom hole reaches the proposed reference wave height. Then the sensitivity is adjusted. Curve method. It refers to the method of using flow detection curve to adjust detection sensitivity. It is also divided into AVG curve and distance amplitude curve sensitivity adjustment. Adjustment of detection sensitivity under AVG curves. For example, the ultrasonic detection sensitivity of forging is, as we can see here, the meaning of this sensitivity refers to the phi 2, the reflect wave height of the flat bottom hole of the reaches of reference wave height. The adjustment method is make the vertical line on the AVG curve through the horizontal coordinate 200, intersecting at phi 2 curve. Make a horizontal line through the intersection point to intersect with the vertical axis, and read out the vertical coordinates with the intersection point. Adjust the attenuator of the instrument until the reading is, at the same time, the sensitivity adjustment is completed, as also we can see here. When adjusting the sensitivity of the distance amplitude curve, it is generally required that sensitivity should not be lower than the evaluation line, and it is specified that when the thickness of the workpiece, as we can see in the formula, the decibel value of the evaluation line corresponding to twice the thickness of the workpiece should be used as the detection sensitivity. As also we can see here, corresponding to delta 1 in the right figure, when the thickness of the workpiece T is more than 46 mm. The decibel value of the evaluation line corresponding to the thickness of the workpiece is used as the detection sensitivity corresponding to delta 2 in the right figure, as we can see. Workpiece bottom above adjustment method. The theoretical formula is as follows. When adjusting the sensitivity with the workpiece bottom wave, first use the theoretical formula to calculate the large flat bottom and phi 2 decibel difference delta of echo from flat bottom hole. Then aim the probe at the bottom of the workpiece, adjust the instrument to make the bottom wave B1 to the workpiece of reached reference wave height, and then use the attenuator gain delta dB. The characteristic of the workpiece bottom wave method is that it does not use a test block, so it need not to carry out transmission compensation like the test block method and the curve method. However, the bottom of the workpiece is required to be smooth and clean, so as not to change the reflectivity of the bottom, resulting in sensitivity deviation. After detection, sensitivity is adjusted. Defects can be quantified. Defect quantification includes determining the size, the number of defects. The size of defects can include the area and the length of defects. As present, in industrial ultrasonic testing, there are many quantitative methods for defects, but they have certain limitations. The commonly used quantitative methods are equivalent method, bottom wave height method, and length measurement method. Among them, the equivalent method and the bottom wave height method are used when the defect size is smaller than the beam cross-section, while the length measurement method is used when the defect size is larger than the beam cross-section. First, we will learn the equivalent method. The defect size determined by the equivalent method is the equivalent size of the defect. The common equivalent methods are equivalent test block comparison method, equivalent calculation method, and equivalent AVG curve method. Equivalent test block comparison method. It is a method to determine the defect size by comparing the natural defect echo in a workpiece with the artificial defect echo on a test block. A series of artificial defect test blocks with different sound paths and different sizes are manufactured. When defects are found during testing, the echo of natural defects in a workpiece is compared with the echo of artificial defects on the test block. When the echo height of natural defect at the same sound path is equal to that of the artificial defect, the size of the artificial defect is the equivalent size of the natural defect. The material surface, finish, and shape of the test block and the tested workpiece shall be consistent as far as possible when using the test block comparison method to quantify defects. The equivalent test block comparison method is the earliest quantitative method, which has the advantages of intuitive and easy to understand, clear equivalent concept, and reliable quantitative. But this method needs to make a large number of test blocks, and the cost is high. At the same time, the operation is quite cumbersome, and it is inconvenient to carry a lot of test blocks for on-site inspection. Therefore, the equivalent test block comparison method is not widely used, and it is only used when x less than 3n or the accurate quantification of particularly important parts. Equivalent calculation method. When the detection distance x is equal or more than 3n, the echo sound pressure variance of regular reflector basically conforms to the theoretical echo sound pressure formula. The equivalent calculation method is, according to the dB value, when the defect wave height measured in the actual inspection reaches the reference wave height. The quantitative method of determining the defect equivalent size is then calculated by calculating the theoretical echo sound pressure formula or of various regular reflectors. The equivalent calculation method does not need any test block for defect quantification, which is a widely used equivalent method at present. Equivalent curve method, which is a method to determine the equivalent size of defects in a workpiece by using general AVG curve or practical AVG curve. The equivalent calculation method and equivalent curve method are described below with longitudinal wave floor dictation as an example. Example 1, as we can see, the 2.5 P14Z probe is used to detect a cake-shaped steel workpiece with a thickness of 4 to 1 mm. The media attenuation is not considered, and the use of the bottom wave to adjust the detection sensitivity is phi2, flat bottom holes. A defect is found at 210 mm in the inspection, and its echo is 226 dB, lower than the bottom wave. Find the equivalent size of the defect. From the topic information, we can conclude is equal to the longitudinal wave velocity in steel divided by the frequency equal to 2.36. Near field N is equal to the square of the chip size D divided by 4 times, equal to 21 mm. Therefore, 3N is equal to 63, less than 210 mm of the defect depth, indicating that the defect is outside of 3N and the equivalent calculation method can be applied. Therefore, from the echo sound pressure formula of large flat bottom and flat bottom hole, the echo sound pressure difference formula of large flat bottom and bottom flat hole at its depth is derived as shown in the figure, as we can see here, where x phi is the defect depth by value 210 mm. xb represents the large flat bottom depth. That is the workpiece thickness value 420 mm. Then the formula of calculating the equivalent diameter of defect is derived from the echo sound pressure difference formula as shown in the figure, as we can see. At last, the equivalent size of the defect is 2.8 mm, calculated by the calculator. If the attenuation of the medium needs to be considered in this problem, the calculation formula is different. As we can see here, the formula, when considering the medium attenuation, the decibel difference of echo between the large flat bottom and the flat bottom hole at different depths is, as this formula shows, indicates attenuation coefficient of the inspected material. Example 2. 2.5 P20Z straight probe is used to detect a steel forging with a thickness of 400 mm. In a workpiece, the longitudinal wave sound velocity CL is 5,900, and a flaw was found at 170 mm in the flaw detection. With the wave height 10 dB lower than the bottom wave, the equivalent size of the defects is calculated by the equivalent curve method analysis. When using the equivalent curve method to quantify defects, it is necessary to draw the flaw detection curve first, as shown in the right figure, and the practical AVG curve has been drawn in this question. Because the title says that the defect wave is found at a depth of 170 mm, and its wave height is 10 dB lower than the bottom wave. It is necessary to determine the decibel value when the bottom wave reaches the reference wave height. So first make a vertical line MN at 400 mm of the apsical to the intersection the B9 at the point M, and then make the vertical line PQ at 170 mm of the apsical to the intersect the Q point with a horizontal line 10 dB lower than the M point. After the Q point is obtained, the defect size can be obtained from the position of the Q point in the AVG curve phi 6 mm. Well, that's all for the class. See you next time.